Last time, we were talking about the energies of the various states in the multi-electron atom. Now, the question is experimentally, how do we know what these energies are? How do we know these energy levels exist? And the primary technique that we have to know that is something called X-ray photoelectron spectroscopy. And X-ray photoelectron spectroscopy uses the same principle that we talked about when we talked about photoemission, or the photoelectric effect, really explained by Einstein. And by the way, I put on the website a very comprehensible article on Einstein's contribution to the photoelectric effect. This is something that just came out in a journal just very recently, and I saw it. And so I urge you to take a look at it, because it really is very understandable and kind of fills in some of the gaps that I left in talking about the actual problems, some of the kind of sociological effects or gaps. Okay? All right, so same idea, photoelectron spectroscopy, in that we come in with a photon, and that induces an electron to be emitted. But unlike the photoelectron spectroscopy on a solid, where we essentially had just one energy level, in photoelectron spectroscopy on atoms, we're going to have many energy levels, as we've already seen. And the photon that we're going to use, that photon is going to have an energy so that, in principle, it can pull out of the atom the most strongly bound electron. And if we want that, well, then that means that we're going to have to use a pretty energetic photon, and that is, we're going to use an X-ray photon. All right? So it works in the following way. Let's take this unsuspecting neon atom. We bring in a photon, an X-ray photon. Turn down a little bit if you can. Not too much. All right, and then that, of course, one of those electrons can be emitted. And one of the electrons that can come off is this p electron here, so that the resulting ion configuration of the neon atom is 1s2, 2s2, 2p5. But also, this photon can pluck off this s electron, so that the resulting ion configuration is 1s2, 2s1, 2p6. And of course, that photon can come in and pluck off an s electron, so that the resulting ion configuration here is 1s2, 2s2, 2p6. All right? So that one photon, in principle, has enough energy to pull off even the most strongly bound electron. And then what we do in this technique is that we measure the kinetic energies of these electrons that are emitted. And then we plot simply the number of electrons emitted at a particular energy. All right, we scan the kinetic energy, and a typical plot looks like this. This is just the number of electrons coming off with a particular kinetic energy. And you see, we see three different kinetic energies. We see electrons coming off with 383 EVs, electrons coming off with 1,205, and electrons coming off with 1,232 EV. Well, of course, it's going to turn out here that those electrons that come off with the lowest kinetic energy are those electrons that were most strongly bound. They are those electrons that were in that 1s state. Why? Well, look at the energy level diagram here. Here are those 1s electrons. Here's the incident energy of the photon that we came in with. If these electrons are most strongly bound, then they're going to have the highest ionization energy, the highest energy to pluck them off. And therefore, in order to conserve energy, the incident energy, the ionization energy, plus that kinetic energy has to equal that incident energy. And if this is the largest energy, well, then those are the electrons that are going to have the lowest kinetic energy. So those are those 1s electrons. That's how we identify those. And then there are electrons coming off at 1205, or those are those electrons from the 2s state. That's a little bit higher energy, right? And so if this is the energy of the incident photon, the photon coming in is the same energy. If that's the energy of the incident photon, this is then the ionization energy for those electrons in that 2s state. Well, that leftover energy then, that's the kinetic energy. And it's a little bit greater than it was for 1s because, again, those electrons are less strongly bound. And then finally, we have this feature here, 1232 eV. Well, those are the 2p electrons. These electrons are least strongly bound. So here's the incident energy of the photon. Here's the ionization energy of those electrons in the 2p state. The resulting, or the leftover energy here is the energy that goes into the kinetic energy of those electrons, and that's going to be the largest kinetic energy because those electrons are least strongly bound. So in this neon atom, we've got 3 different states with 3 different energies. That is reflected in the fact that we're going to have, in the photoelectron spectrum, we're going to have 3 different kinetic energies for the electrons coming off. So by looking at the photoelectron spectrum, you can immediately tell how many energy levels you've got. And, of course, as the kinetic energy goes up, well, that means that the binding energy goes up. The binding energy gets more positive, right? Meaning the electrons are less strongly bound. Or another way to put it, as this kinetic energy goes up this way, the binding energy gets more negative this way, right? The electrons are more strongly bound as that binding energy gets more negative. All right? Okay. But from this kind of experiment here, we can extract what these ionization energies are, and we can extract then what the binding energies are. Because of conservation of energy, incident energy of the photon equals the ionization energy plus the kinetic energy. I can rearrange this to calculate the ionization energy. I did that for all of these 3 features. Here is the incident energy of that X-ray photon. Here's the measured kinetic energy. The difference between the 2 is the ionization energy. I solved for that there. And then that ionization energy, we know, is minus the binding energy. So if the ionization energy is 21.6 eV, the binding energy here for that 2p electron is minus 21.6 eV. And for 2s, minus 48.4 eV. And 1s, minus 870.2 eV. Okay? I want you to notice how much more strongly bound that 1s electron is than the electrons in the n equal 2 shell. Look at that. That 1s electron is bound by 870 eV. Binding energy is minus 870. Binding energy for the n equal 2 electrons is minus 48 and minus 21. Right? Why is that more strongly bound? Well, this electron is in the n equal 1 shell, which is much closer to the nucleus, where the attractive interaction between that positive charge on the nucleus and the electron is much greater. All right? Okay, so this is basically the technique. This is how we calculate those binding energies or observe those binding energies for the electrons in the multi-electron atom. Okay, great. So what I want to do now is want to start on today's lecture. And you don't have the lecture notes for today's lecture. And there is a reason for that. Oh, and I forgot to tell you to do something. Oh, very important. Okay. I'm going to start on today's lecture. And through this lecture, I'm going to be asking you some questions. And you're going to have the opportunity to answer. But the way you're going to have the opportunity to answer is that you're going to have to make some paper airplanes. And so I'll ask a question, and then I'll say launch. And what you have to do is you have to throw the paper airplane to the board. And the first paper airplane that hits the board from that section, well, that section gets a chance to answer that question. And we're going to keep score. And we've got some treats for the winning section. Okay, so the TAs have some scrap paper, and they're going to pass that out. And so you can be making some paper airplanes. Write the number of your section on the paper airplane. Also, some of you are not strategically located to hit the blackboard. If that's the case, why don't you select somebody from your recitation to be the launcher? They can come down as close as these few stairs and aim at it for your section. Okay? Okay, so I'm going to start talking. We're going to talk about the periodic table and the trends in the properties along the periodic table. And of course, it's the electron configurations that allow us to understand the structure of the periodic table. But it is important to realize that the periodic table was first assembled by Mendeleev and other people, not on the basis of knowledge of the electron configurations, but on the basis of knowledge of the similar properties, similar chemical and physical properties of the elements. So for example, lithium, sodium, potassium here, they were all grouped in one column because they were all found to be very soft, malleable metals that were very reactive. Helium, neon, argon, they were all grouped in one column because they were found to be very inert, very unreactive. And of course, now we understand the electron configurations, why these elements have the similar properties. In the case of the alkali metals, lithium, sodium, potassium, hey, we got that extra X electron, that unpaired electron that makes those metals very reactive. In helium, neon, argon, we've got an inert gas shell configuration that makes those elements very unreactive. But by the late 1800s and the early 1900s, the similar chemical properties of atoms in a column of a periodic table, that really was strongly believed to an extreme. So for example, it was known that human beings consumed sodium, salt. It was known that human beings, our bodies contained sodium ions and potassium ions. So, well, if our body has sodium in it and potassium in it and we consume those two elements, why not a little bit of lithium? Okay, so about 1925 or so, a soft drink came on the market. And that soft drink, they wanted to have a lemony flavor to that soft drink. And so how do you get a lemony flavor? Well, you use citric acid. But citric acid isn't really soluble in water, so hey, we got to make a salt out of the citric acid. So, hey, for whatever reason, a lithium citrate was made. A lithium salt of citric acid was made. And that soft drink was none other than 7-Up. All right? And in fact, if you look here, it tells you that the lithium was touted to give healthful benefits, including an abundance of energy, enthusiasm, a clear complexion, lustrous eyes, or lustrous hair and lustrous eyes, shining eyes. And so this was on the market until the early 1950s, when finally the antipsychotic properties of lithium were being discovered, and the side effects of lithium were being discovered. And the 7-Up was then taken off the market, or at least the lithium citrate in the 7-Up was removed from the market. And of course, it wasn't until the early 1970s that lithium was approved as an antipsychotic drug, because it really is poisonous to the human body in large amounts. And so I really don't know, how many individuals had side effects from drinking 7-Up at that time. But the moral of the story is that even though we're about to talk about some of the general trends in the periodic table, don't put any element in your mouth just because it's in the same column as some element you do put in your mouth. Okay. True story. All righty, so one of the properties we're going to talk about is the ionization energy. And we've talked about it already, but we haven't formally defined it. Let me do that here. Here you see boron with its electronic structure going to boron plus. The energy change for this reaction is what we call the ionization energy. It's the products minus the reactants. That's the ionization energy. Equivalently, that's the ionization. That ionization energy is minus the binding energy of the 2p electron in boron. This is a process that it's removing the least strongly bound electron. When we remove the least strongly bound electron, the energy that is required to do that is called the ionization energy, and more fully, it's the first ionization energy. It is the energy to remove the electron from this HO8O is the highest occupied atomic orbital, all right, or the least strongly bound electron. Same idea. This is highest occupied atomic orbital. This is the highest occupied atomic orbital. Now, generally, when we say ionization energy, we mean the first ionization energy. We often leave out the word first. All right? So whenever you look up an ionization energy, implied in that is that it is the first ionization energy, the energy to remove the least strongly bound electron. The second ionization energy, well, that's the energy required to remove another electron. But now we're removing it from boron plus to make boron plus 2. And again, we're removing the next least strongly bound electron. That's the second ionization energy. Equivalently, it is minus the binding energy of the 2s electron in boron plus, not boron. And then there's a third ionization energy. Again, now we're taking boron plus 2, pulling off the next least strongly bound electron to make boron plus 3. That's the third ionization energy. And we can keep going. Boron plus 3, pull off the next electron. Boron plus 4, that's the fourth ionization energy. And then the fifth ionization energy, taking the last electron off of boron, boron plus 4 to make boron plus 5. That's the fifth ionization energy. All right? So these are our definitions here of the ionization energy. Now I'm going to switch to the side screen. Okay? Yeah, great. All right. But now, here comes the first question. I'm going to show you two reactions here. The first reaction is a boron plus going to boron plus 2. We are removing here an s electron. The second reaction here is boron going to boron plus. Again, we are removing a 2s electron. And the question is, are these two energies equal? In both cases, we're pulling off an s electron, a 2s electron. Okay? So that's the question. Now, the way we do this is I'm going to move to the side. I'm going to say launch. And then Christine and I will try to determine the first airplane to hit the board. We'll pick it up and we'll ask that recitation section to answer. All right? Ready? Launch. Recitation 1. Are those energies equal? Answer? It can be a group effort. Hey, you got a 50% chance here. Yes or no? No, they're right. They get a point. Okay, you got to keep score on the board. All right. Now, why aren't they equal? Hey, big no here. They are not equal because, in this case, this is the ionization energy, the second ionization energy as we just defined it. Right? Boron plus going to boron plus 2. That's the second ionization energy. It's minus the binding energy of the 2s electron in boron plus. Here, this energy, what this energy is the ionization energy of the 2s electron in boron, not boron plus. This is equal to minus the binding energy of the 2s electron in boron. This is minus the binding energy of the 2s electron in boron plus. They're not equal. The next question is, which one is greater? All right? And so wait a minute. Wait, I'm going to get out of the way here. Okay? Launch. Recitation 9. Recitation 9. Over there, sorry. Which one is greater, top one or bottom one? Top one. They are right. Hey, recitation 9 gets a point. You can put on the score on the board. That'll probably be okay, great. The top one is greater. The top one is greater because the effective charge of this 2s electron in boron plus is larger than the effective charge of the 2s electron in boron. The reason for that is because in boron plus we have fewer electrons. We've got less shielding of the nucleus by the electrons because we have fewer electrons. Okay? So that's great, but this is really very important for you to understand here. This will be on the lecture notes that I will give to you at the end of the class. Because we might run out of paper, you might want to save those. Yeah. Okay? Yeah. Okay. All right, so now we're going to look at the periodic table here. And I'm going to ask this following question here. As we go across the periodic table, what we want to know is, no chalk. What we want to know is how does the ionization energy change? So here's my periodic table. So I'm going across this way. Does the ionization energy increase or does it decrease? All right? Now, here's another chance for you to answer this for your recitation section. Launch. Hey. Wads don't count. Wads don't count. Wads don't count. Paper airplanes. 8. Where's 8? Back there. Hey, okay, 8. What happens to the ionization energy as you go across the periodic table? What? Increase. Is that your final answer? You're right. All right, the ionization energy increases. Okay, why does that ionization energy increase? Here's our example. Here's our plot. Ionization energy versus Z as you go across. Here is from hydrogen to helium. That's one row, goes up. Here's from lithium to neon, another row, it goes up. Well, the ionization energy increases because the nuclear charge increases, right? As you go across the periodic table, the nuclear charge increases. The Coulomb interaction increases. But there's another part to the Coulomb interaction. And of course, that other part is the distance. But as you go across the periodic table, you're putting electrons in to the same shell, to the same principal quantum number shell. And in general, when you put electrons into the same principal quantum number shell, hey, you are, on the average, the same distance away from the nucleus, all right? And so R is the same. Z is increasing as you go across. And so, therefore, that ionization energy increases as you go across the periodic table. Now, however, you can see that there's some glitches, right? There's a glitch here between beryllium and boron. Boron is actually a little bit lower in ionization energy than beryllium. Can we understand that? Well, we sure can in terms of the electronic structure. So here is the electron configuration of beryllium, Z equal 4. And then here is the electron configuration of boron. All right, this is 1s, this is 2p, Z equal 5. The bottom line is that it takes more energy to put the next electron here into this 2p state. And the bottom line is that if a charge on the nucleus does not increase sufficiently to fully compensate for the energy that is necessary to put that next electron in that higher energy state. All right? So this just doesn't get large enough, fast enough to compensate just for the extra energy that's needed to put that electron in the 2p state. So we have a little glitch between beryllium and boron. In addition, we got a little glitch right here between nitrogen and oxygen. The oxygen ionization energy is not as large as you might expect from the increase in the Z Z quantum number. So again, here's the nitrogen, Z equals 7, the electron configuration for nitrogen. Here it is for oxygen. All right? And what we had to do for oxygen is that we had to put another electron into a 2p state that already had an electron in it. And there's a great deal of repulsion here between these two electrons in the same state. And again, the Z here, the nuclear charge, didn't increase large enough or greatly enough to compensate for that electron-electron repulsion. And so the ionization energy is just a little bit lower than it is for nitrogen. That same trend, of course, continues for the other rows in the periodic table. Here is the third row. And there's also a glitch between magnesium and aluminum. Magnesium and aluminum are right below beryllium and boron. And a glitch between phosphorus and sulfur. They're right below nitrogen and oxygen. Okay? Okay. Next question. As we go down the periodic table, what happens to the ionization energy? All right? Wait a minute, I'm getting out of the way. Okay, ready? Go. All right. Recitation 1. What happens to the ionization energy as you go down the periodic table? Decrease. Yes, they're right. Okay, why does it decrease? It decreases as you go down the periodic table. Z is increasing. That is true. But as you go down the periodic table, you're putting electrons into shells that on the average are farther out from the nucleus. And so as you go down the periodic table, it's that distance dependence that dominates the ionization energy. So across the periodic table, ionization energy increases. Down, it decreases. Across, it's Z dependence that dominates because R is constant. As you go down, it is the R dependence that dominates. That's changing. Even though Z is changing, R changes faster than Z. Okay? All right, great. Now, let's talk about another property here. And that other property is called the electron affinity. So if I take a chlorine atom and I add an electron to it to make Cl minus, the energy change for that reaction is minus 349 kilojoules per mole. That is, the chlorine ion is more stable than the chlorine atom. This is a reaction that releases some energy. Okay, now, the question is, there's a quantity called electron affinity. You need to define the electron affinity. Okay? All right, so, are you ready to launch? All right, launch. Four. Recitation 4. You're up there, right? All right. Can you define the electron affinity? What's the electron affinity equal to? I'm going to write this. Electron affinity is equal to what? Yes? Answer? Yes, that's great, but I want a mathematical definition here. EA equals negative IE. No. All right. You got to do another launch. Ready? Launch. Recitation 1. What is the electron affinity equal to? Answer? Beep. Oh, what is it? No. Next launch. Ready? Launch. What is it? 9. What's the answer? What's the electron affinity equal to? Beep. What? Yes? Keep going. ionization energy. Okay, the electron affinity here is minus this energy, right? If you add an electron to an atom, there's an energy change. The electron affinity is defined as minus that energy change. Okay, great game. We didn't get very far. However, from these scores, recitation section 1 has does win. Okay, I'll see you on Monday.